Hey class, welcome back. This is part 2 of the project management chapter. Right now we're dealing with uncertain activity times, and this video will make no sense unless you've watched part 2, or part 1 rather. Where we're at now, the slide you're looking at here is the result of going through the earliest start, earliest finish, latest start, latest finish activity that we did in the first video of this week's material. What they did is they used the um, the A plus 4M plus B. Let's see if I can back up and show you that. They used that. They used this formula, A plus 4M plus B divided by 6, in lieu of a deterministic time, and they used that together with the precedent diagram that you're seeing here. In order to go through and determine the earliest start, earliest finish, latest start, latest finish, and in that process you'll recall you're able to determine your critical path. So the result of all that is on this particular slide here, and you see these activities with zero slack. In other words, the earliest finish is the same as the latest finish. There's no wiggle room. It's critical that these activities get completed on time in order to get the project done on time. And the result of that is that activities A, C, F, I, and K are on the critical path. So A, C, F, I, K, I'll write that down here. Let's erase this. A, C, F, I, K are the critical path activities. Let me erase all this that we were dealing with earlier. Okay, let's see. Now, let's go back and let's figure out what the expected times and the variances were for A, C, F, I, and K. Okay, I'll do that right here because I'm only now interested in those critical path activities. Why? Because those are going to serve as a proxy for completing the entire project. In other words, if we were able to complete the critical path in a particular period of time, then we're saying we're able to complete the entire project in a particular period of time. Okay? So let's look at these. A, C, F, I, and K have expected times of 6, 3, 4, 5, and 5. 6, 3, 4, 5, and 5. 6, oops. 6, 3, 4, 5, and 5. Those are the expected times that I'm going to complete activity A, C, F, I, and K. 6, 3, 4, 5, and 5. Let me toggle back. And let's record the variances. I may need to shrink this here. Okay. 4/9, 0. See if it'll let me write on here. Nope. 4/9, 0. Let's see, F-I-K. F, the variance is 1/9. I is 1 and 4/9. So 1/9, 1 and 4/9. Okay, so 1/9, 1 and 4/9. So this is the expected time, and this is the variance. Okay. So we learned how to compute the expected time. This 6 here is simply the pessimistic plus 4 times the most likely plus the optimistic. Divide that all by 6 and you get 6. The variance, recall, we take the pessimistic, we subtract the optimistic, we divide that number by 6, and then you square that, and that's where that 4/9 came from. Okay, so we went over that in the previous video. Now we have computed the expected time and the variance for each of those items on the critical path. We use these numbers here to, along with all of the expected times for all of the activities, along with the precedence diagram, to figure out what the critical path was, and we now know that that's the critical path. Okay, what do you do with this? Well, we can add this up to determine how long the project should take. And we got 6 plus 3 is 9, plus 4 is 13, plus 5 and 5 is 23. So we now think that this project should take 23, let's say, weeks. Now, what we can do also, we haven't talked about this yet, is we can compute the critical path's variance. So I can add these up. 4/9 plus 0 plus 1/9, that'd be 5/9, plus another 9/9, 14/9 plus 4/9 is 18/9. So if I add these up, I get 2. Okay, so the variance of the critical path, let's write it like this, A, C, F, I, K, is going to equal 2. Where'd the 2 come from? 4/9 plus 0 plus 1/9 plus 1 plus 4/9. Okay? So the variance of the duration of the critical path is 2, and the expected duration of the critical path is 23. Simply the expected durations of the activities summed. Okay? Now, what do you do with that? Well, I want to convert this to a standard deviation. So I just take the square root of each of these. So now I have the standard deviation of ACFIK equal to the square root of 2. And off the top of my head, I don't remember what that is, but it's like 1.4-ish. Let's see. I'm going to pause that. We'll get an exact number, and then I'll show you what we can do with that. Okay. The square root of 2 is 1.414. And so what we have in that number, 1.414, is an estimate of the standard deviation of the duration of the critical path, and we're using that as a proxy for the standard deviation of the duration of the project. Okay, so now we know some things. We say this project ought to take 23 weeks with a standard deviation of 1.414 weeks. Now we can do some things. Now we can do some very useful things with that information. Let me erase some of this and we will work with those numbers. Now, if somebody says, what's the likelihood that you'll be able to get this project done in 23 weeks? What would your answer be? Your answer should be 50-50. Because what they're saying is, I've lost my pen. Hang on a minute. You are getting the real life experience of Bob here. No polished video here. I lost my marker. Okay, now then, what they're saying is if you say what's the likelihood it gets done in 23 weeks, that's the mean, and they're talking about this area right here. That area that I just shaded corresponds to the likelihood that we would get done in 23 weeks. And that area right there is 50% of the total area. And another way of saying that is there's about a 50% chance that we'd get this project done in 23 weeks. Okay? If they said to you, what's the likelihood that we could get this project done in, let's say 26 weeks? Well, 26 would be, 3 weeks out, which might be about right here. 3 weeks in addition to what we expect. So 26. Let's figure this out. How many standard deviations is 26 from 23? Well, each standard deviation is 1.414. So if we go out one standard deviation, and we're right here, we're talking about 24.414. If we go out 2 standard deviations, now this little point right here is 25.828. Okay, so if we go out to 26, we're 3 weeks past the mean. Each standard deviation is 1.414. So we are, a little bit more than 2 standard deviations from the mean. We need to calculate that. We take the difference between the 26 and the mean, 23, which is 3, and we divide that by the size of a standard deviation, and that tells us the distance from here to here in standard deviations. Okay, so let's calculate that real quick. Okay, when we calculate that, we find that 26 is 2.12 standard deviations away from the mean. And what you're going to need to do now is we're going to need to pull out our textbooks and look at our appendix that gives us the areas for the standard normal distribution. And if you look at that, it should be Appendix A in your textbook. And you're going to see, probably want to pause the video and go get your textbook or find this areas for the normal standard distribution. And you'll see a legend at the top. And that legend should look like this. And it'll show a shaded area right here. Okay? And then you have a table, and you have a little Z here. That's supposed to be a Z, not a 2. And then you have numbers going across and numbers coming down. Okay? And then you have, of course, numbers in the body of the table. Well, what we're going to do is we're going to find 2.12, and we're going to do that by coming down this Z column until we get to 2.1. So we're going to find 2.1 down here. And what you do is you add the row heading. In this example, it's 2.1. You add the row heading to the column heading. So we're looking for 0.02. Okay, so that'll be about right here, 0.02. And we're going to come down here and over here, and we're going to find the number at the intersection of that. So that's 2.1, the row heading, 0.02, the column heading, and we're going to look at the intersection of that. We're going to add the row heading to the column heading, that's 2.12. Of course, where'd that come from? Right here. And the number at the intersection there is 0.4830. 0.4830. Okay? I didn't think I left enough room in there, but 0.4830. So that's supposed to be 4830, 0.4830 right there. Okay, what does that mean? Well, that means this shaded area right here is 0.4830. Okay? Now, if that shaded area is 0.4830, if we look at this entire area, now I shade the left-hand side over here as well, and now we consider that total area, that would be 0.98. Okay? A little more than 98% of the total area under the curve. Okay? Now what that means is if I come here and I shade this entire area, then this shaded area from 26 weeks to the left, from 26 weeks or fewer weeks, that's 98.30% of the total area under the curve. And what that means is, if you haven't figured this out already, you probably are ahead of me, that 98.3% of the time, when a project averages 23 weeks with a standard deviation of 1.414 weeks, 98.3% of the time that project is done in 26 weeks or less. So if someone said, what's the probability of completing this project in 23 weeks? You would say 50%. What's the probability of getting this project done in 26 weeks? You could calculate that and you would find that it is 98.30%. And I'm going to leave it right there.